Oh yeah. So about the psi of x minus a, which in three-dimensional. Not sure how to properly say what it is. Like, the wave function under spatial transformation.
Right.
So in 3D, I'm not sure how to show this exactly. It's like, can you give me some hints? So
Oh, I
it's
see. Right. Yeah, yeah. Okay, just let me open my note. Okay. Sorry, আমার নোটও হচ্ছে গিয়ে there are so many notes that it's hard for me to find the right note. Last class was, I think that's the one. Yeah. All right.
Sir,
Yeah.
are you like using your iPad? The screen is stuck, I think.
No, it's not stuck. I haven't written anything.
Acha, acha.
Yeah. Okay. Right. So the question is that how do you show that psi of x plus a is equal to e to the power minus I h bar, the momentum operator dotted with the translation vector acting on psi of x. So, first you have to, Josh, is your answer related to whether, how do you show this? Or the technical bits that come after that? Josh?
Oh, sorry, I was muted. After that, yeah.
Okay, so yeah, I mean, once you've convinced yourself of this, then the rest is not very difficult. So then you do is that you think of this as a function of three variables, x1, x2, and x3, right? So when you simultaneously express psi as a Taylor series in terms of three different variables. So you'll get three terms in the expansion at a linear order. And the three terms is going to be, they're going to be summed. And so we are assuming that this is a small quantity and the summation will be delta A. So there are three terms here and dotted with the gradient of psi at x and then higher order term. So you see that, what is this? This is, if I break it into component, this will be x1 delta A1 del by del x psi plus delta A2 del by del y of psi plus delta A3 del by del z of psi, right? This is what we call, what we're writing here. এবং তারপরে, it's kind of easy because then you just say, okay, I'm going to multiply this by I by h bar and divide by I by h bar. So I get something like, what is it, minus I by h bar or plus, anyway, that's, and then it's minus I h bar, right? And here it will be, this will be dotted with the gradient of psi. Sorry, let me just, put the bracket here, right? So what is, and what is this thing? This is just the momentum operator, the three-dimensional momentum operator, right? So this is basically, and this is the infinitesimal thing. But you see momentum operators, like one component of the momentum operator commutes with all the other components of the momentum operator, right? This is equals to 0. So, there is is that you can apply consecutive momentum operator, without any problem. So you can build up a finite translation by applying an infinite number of infinitesimal translation, and that's how you get. And then playing with the sign a little bit, you get the translation of psi is given by e to the power minus I by h bar a dot p acting on psi of x. Okay.
Yeah, I was thinking how the exponential came, so I guess I'll have to look into that again.
So exponential is just like this is something you should have learned in your math class. Is that one? If you take a and then x by n to the power n, and in the limit where you take n to infinity, this becomes e to the power x, right?
Yeah, I completely forgot about that.
Sir,
so
could you please briefly recap what the previous expression is about? I believe it's from last class, right?
this one,
Yes, this one.
yeah. Just give me 1 second, okay? Let me just turn on the AC. It's very hot in here. So Wajia is asking what this expression is about. So that's a very good question. So the idea is something like this. Suppose you have some sort of system that you're doing experiments on, right? So you have some box, say, I'm just making this up, okay? And you have some quantum system, say a particle or something, and you're measuring its property. So it's described, this quantum particle is described by some wave function. Say this is your xy, there's a z-axis, but I'm not going to draw it. And of course, its wave function is a complex number, but I can only draw a real function. So this is, the z-axis is the wave function. Okay, now what I do is that suppose, the chairperson of the department comes and says, he kicks me out of my room.
Sir, do we not write the modulus of psi squared usually?
I mean, no. I mean, this. All I'm saying is the wave function has an imaginary component as well, but I'm not drawing.
I mean, like when we draw draw it in a graph, we usually do that because it's
Yeah, but I'm not doing that. I'm just drawing it
just
as
the real part of psi.
Yeah, I'm just drawing the real part of the psi. Just imagine in your mind there's a imaginary part as well. Okay, so I'm not computing its probability. I'm just computing. If you like, I can say, okay, this is the real part, and there is an imaginary part, which is a little bit different. Okay, so imaginary. Sorry. Okay, so that together they give you the wave function. So now what happens is that the head of the laboratory comes and says, "Oh, move to the next room." So then what I'm going to do? I'm going to translate my experiment to the next room, right? Suppose the next room is the distance to the next room is a. That's the displacement vector, right? So once I move my system to the next room, this wave function will no longer be given. The wave function of the system will no longer be given by this guy. It will be given by psi, so a new wave function, and it's in its new position, right? Now what I'm trying to figure out is that how is this related to the old function, wave function that I had in my previous room? And what this formula tells me is how the and what is this Now, okay, so what we have established previously is that, just by a heuristic argument, that in principle, the old wave function is related to the new function through this, relationship. Okay, that's something that we have argued. Now, what we are trying to do now is that suppose that I give you, just this wave function, and you didn't know about any of this, and how could you find what the wave function would be after you move to a different room? The way you do it is that you apply to your old wave function, this operator. Then you find a new function which gives you the it's actually the old wave function with the argument shifted, right? So that gives you how the description of the system has changed. Okay, so this formula is telling you how, given a wave function at some spatial point, you can find the wave function of the system at a different spatial point. This is analogous to if I gave you the wave function at a given time. Sorry, there should not be a bar here. You should be how you find the wave function at a different time. Okay. Depending on what your wave function is, this this translation can be quite non-trivial, right? But does that answer your question?
Yes, sir. I think I get what you're trying to do.
Right. So, I mean, there are many various. I mean, it's in some sense a very deep question. And let me just say in another word. Suppose that this is our universe. This is what physics is about. Suppose this is our universe at some given time. Okay, so at some time, let's call it t0. This is the spatial slice of our universe. And suppose that we know all the information about the universe at this time, which is given by some wave function psi of t0. Okay. So what is physics? Physics is really about either predicting the future or predicting the past, or post-dicting the past. I don't know how you want to call it, right? You want to know if you knew the wave function of the universe at this moment. Usually you don't know the wave function of the universe. You know a subset of the wave function of the universe, and you know what the boundary condition to that subset is, so you can predict the future of that universe. So what you want to know is that at a future time slice, suppose this is the future time slice, where t is equal to, say, t1, what would the universe look like? So what psi looks like at t1. So what you have to do is that you have to solve the Schrodinger equation. So what do you need for this? You need the wave function of the universe at a given time, t0. You need the Hamiltonian of the universe. And then suppose that the Hamiltonian of the universe is time independent. Then you solve the Schrodinger equation. What does that solving the Schrodinger equation imply? It implies calculating the time evolution operator. Okay, so you want to calculate t1 minus t0, which is going to be e to the power minus I h bar Hamiltonian t minus t0. This is what it means to solve the Schrodinger equation, to actually be able to calculate this. And then what you do is that you apply this time evolution operator to the wave function of the universe at this particular time. And then you get from that the wave function of the universe in the future time. And you can say, okay, you see the wave function of the universe is saying that there's a star here and there's a star here. And, because you have a super duper computer, it's going to tell you that star is going to form, and you have solved, suppose you have solved quantum gravity and all that. So the future of your, the wave function of the future wave function of the universe is going to tell you that, this star has actually formed a black hole, and this has become a neutron star, and that they have actually collided, and that they're going to give out some gravitational waves. And suppose the Earth is here, so you can say, okay, you can calculate how long the wave function of the will come, and then you can then predict, right? So, and similarly, if you knew the wave function of the universe at the present time and you knew this operator, you could calculate, what the wave function of the universe would be at a past time, say t equals to, say t1 prime, where t is, or say minus t1 prime, where we are taking t to be t1 prime to be a positive number, right? And you could also calculate that. So if you knew the Schrodinger how to solve the Schrodinger equation, you could also predict. So this is what evolution means in terms of a unitary operator. So similarly, suppose that something about the what the Hamiltonian of the universe looks like, and the momentum, everything about about your system, because H and P, the momentum operator, and then what the universe, the wave function is at a given spatial slice, say x1, and you want to find out what that wave function looks like at a spatial slice x prime. Then you evolve this guy in this direction now, but instead of using the time evolution operator, you use the translation operator to find from the wave function at this, in some region, to the wave function in a different region, okay? So, but of course you have to, so this is basically the same philosophy, whereas the time evolution operator evolves your system in time, the translation operator evolves your system in space. Okay? Radhika, what do you think?
This was a lot, but yeah, I think I